Hello students, it's me Praveena. I'm here with a new topic, mechanical rotational system. And we all know that we have discussed in the last class about the mechanical translational system, and we have discussed two of the problems, and I have given two problems for you as homework. Okay, I think you all have gone through those sections. Okay. So next we will discuss about mechanical rotational system, and it is also similar to the mechanical translational system, but there is some difference between the notations used for mass, displacement and spring, etc. Okay. So we will discuss the details about mechanical rotational system. So first of all, we have a look at the basic components in a mechanical rotational system. So the model of rotational mechanical system can be obtained by using three elements, and these three elements are moment of inertia of mass, that is represented by the letter capital J. Second element is dashpot, and that is represented by the letter B, and the dashpot has a frictional coefficient B, and the third element is torsional spring with stiffness K. So a mechanical rotational system is represented by three elements: moment of inertia of mass, dashpot with the rotational spring coefficient B, torsional spring with stiffness K. Okay. In the mechanical translation system, we are using the mass M and dashpot B and spring constant K. Okay. In mechanical rotational system, we are using, instead of mass, we are using moment of inertia, that is represented by the letter J, and a dashpot we are representing it with the same letter B, and torsional spring with K. Okay. And the weight of the rotational mechanical system is represented by the moment of inertia of the mass. The moment of inertia of the system or body is considered to be concentrated at the center of the gravity of the body. The elastic deformation of the body can be represented by a spring or torsional spring, and the friction existing in rotational mechanical system can be represented by the dashpot, and the dashpot is a piston rotating inside a cylinder filled with viscous fluid. Okay. You got the idea that in the case of rotational system, we are not using the term mass. Instead of that, we are using moment of inertia, and we are considering that this moment of inertia is concentrated at the center of gravity of the body. Also, same in the case of mechanical translational system. Here also, that is in mechanical rotational system, the elastic deformation of the body is represented by this spring, and that is represented by the constant K, and the friction existing in the rotational mechanical system is represented by the dashpot, that has a coefficient B. So when a torque is applied to a rotational mechanical system, it is opposed by opposing forces, or here we are using the term torques instead of force. Okay, when a torque is applied to a rotational mechanical system, it is opposed by opposing torque due to moment of inertia, friction and elasticity of the body. So there will be opposing torques due to moment of inertia of the body, and there will be opposing torque due to friction of the body, friction of the spring, and there will be opposing force due to the elasticity of the system. So the torques acting on a rotational mechanical body are governed by Newton's second law of motion for rotational system, and this law states that the sum of torques acting on a body is zero, or Newton's law we can state that the applied torques is equal to the sum of opposing torques on the body. So in the mechanical translational system, we are representing the total force acting on the translational mechanical systems are governed by Newton's second law of motion. Similarly, in the case of mechanical rotational system, the torques acting on the rotational body is governed by the Newton's second law of motion. But in previous cases, we are giving the equation as a sum of forces will be equal to, algebraic sum of forces will be equal to 0, and here we are saying that the sum of torque acting on the rotational mechanical body is equal to 0. So there is a connection, that is why I said that there is a connection between mechanical rotation and translation system. Usually the analysis, both of the system analysis is in the same manner, but the notations used here is different. Okay. So it will be easier to study mechanical rotational system once you go through the portions of mechanical translational system. Okay, so you should first thorough the mechanical translational system, then it will be easier to do problems in the mechanical rotational system also. So let us start with the list of symbols used in the mechanical rotational system. Okay, the list of symbols used in the mechanical rotational system is given as, first is theta, that represents the angular displacement and its unit is radians. And next is d theta by dt, that is angular velocity and its unit is radian per second. Next is d square theta by dt square, and that is angular acceleration whose unit is radian per second square. Next is torque, that is applied torque, that is represented by capital letter T and its unit is Newton meter. And next is capital J, that is moment of inertia and its unit is kilogram meter square per radian. And next is B, that is rotational frictional coefficient, its unit is Newton meter per radian per second. And next is K, that is stiffness of the spring whose unit is Newton meter per radian. So this is the list of symbols used in mechanical rotational system, that is theta, d theta by dt, d square theta by dt square, capital T, capital J, capital B and capital K. So 7 symbols are using here. And in the case of, you should remember, in the case of mechanical translation system, what are the symbols used? You know that it is, instead of theta we are using x there, instead of d theta by dt we are using dx by dt, instead of d square theta by dt square we are using d square x by dt square there, instead of t we are using capital F there, instead of j we are using capital M there, and for B and K it is same. Okay, so that is a comparison, so it will be easier, so this topic will be easier for you. So these all are the symbols used in mechanical rotational system. What are the symbols? Theta, d theta by dt, d square theta by dt square, t, j, b and k. These all are the symbols used. Okay, so next is torque balance equations of idealized elements. What are the idealized elements? Idealized elements are moment of inertia or mass J, and dashpot with coefficient B, and next spring with stiff constant K. Okay, so these are the idealized elements. So we are now discussing about the torque balance equations of idealized elements. So first of all, we discuss about the mass. So consider an ideal mass element. Here the mass element is J. So when we are discussing about a mass element J, we are assuming that it has a negligible friction and elasticity. So here in the rotational system, instead of mass we are using the term moment of inertia. So it is represented by J, and here in this figure, in this mass element, an applied torque T is acting. Due to that torque, there is a displacement theta. Since it is a rotational system, we are representing the displacement as angular displacement. Okay, that is why we are using the notation theta. But in the case of mechanical translational system, the displacement is linear. So we are using the notation x. Okay, that is the connection. So in mechanical rotational system, since it is a rotational system, the displacement will be angular displacement. So we are using the term theta. Okay, here these all are the parameters. So when we are representing the torque balance equation for the idealized mass element with a moment of inertia J and applied torque T and angular displacement theta, we can say that T is the applied torque. Okay, capital T is the applied torque. Next, due to the moment of inertia or mass of the body, there will be an opposing torque. That torque is represented by T suffix J. Okay, so due to the mass of the body, there will be an opposing torque. That opposing torque is represented by T suffix J. So T suffix J, that is Tj, is the opposing torque due to moment of inertia of the body. So by Newton's second law, we know that the opposing torque is directly proportional to acceleration. and that is here we can say it is angular acceleration. So the opposing torque due to moment of inertia of the body is directly proportional to the angular acceleration. So we can write the equation Tj is directly proportional to d square theta by dt square, or Tj equal to j into d square theta by dt square. So by Newton's second law, T we can write applied torque is equal to opposite torque, that is applied torque is capital T and opposite torque is Tj. So T equal to Tj equal to j into d square theta by dt square. So this is the torque balance equations for the ideal rotational mass element, okay, having a moment of inertia j. So this is the case of a rotational system. So here T equal to Tj equal to j into d square theta by dt square. In the case of mechanical translational system that we have discussed in the previous class, what was the equation for a mass element? F equal to Fm equal to capital M into d square x by dt square, okay. So you should remember that case also. That is why I am saying both the cases. So now we are discussing about a mechanical rotational system, but the mechanical rotational system is similar to the equations are similar to that of the mechanical translational system. So you can study both very easily, okay. So first is we discussed about the mass element. What is the next element? Next is the dashport, okay. So next we can consider a ideal frictional element dashport, okay, and that dashport is shown in this figure in the rightmost uppermost part, okay, rightmost uppermost part there is a dashport shown, and the applied torque on that dashport is capital T, that is shown, and due to that applied torque T there is an angular displacement theta that is also shown there, okay. So we can write for the frictional element, for the ideal frictional element dashport, and when we are considering it, we are assuming that it has a negligible moment of inertia and elasticity, and we are applying an applied torque capital T on that. So due to that applied torque on dashport, there will be an opposing force in that dashport, okay. Due to the applied torque T, there will be an opposing force on the dashport, and that can be represented as capital T suffix B, okay. So TB is the opposing torque due to friction in the case of dashport. So we can write the torque balanced equation. We know that in the case of a dashport, TB can be written as TB is directly proportional to angular velocity, okay. That is TB is directly proportional to d theta by dt, that is equal to TB is equal to capital B into d theta by dt. So by Newton's second law, the applied force is equal to applied torque is equal to opposing torque, that is T is equal to TB, that is equal to B into d theta by dt. That is the torque balance equation for a dashport or frictional element, that is T equal to TB equal to B into d theta by dt, okay. So in the case of translational system, similar to dashport, in the case of dashport, it is F equal to FB equal to B into dx by dt. So in the case of rotational system, it is T equal to TB equal to B into d theta by dt, okay. In the case of mechanical translational system, applied force is equal to opposing force is equal to B into dx by dt, okay. But in the case of mechanical rotational system, it is torque equal to applied torque equal to opposing torque, that is equal to B into d theta divided by dt, where d theta by dt is the angular velocity, okay. Suppose when the dashport has an angular displacement at both ends, and that angular displacement is shown in the second figure, okay. That means here when we are applying an applied torque, due to that applied torque there are displacement at the both ends of the dashport, and here it is shown that theta 1 is the displacement at one end and theta 2 is the displacement at the other end, okay. Theta 1 and theta 2 are the displacement at both ends. So in that case we can write the torque balanced equation as it will be directly proportional to the differential angular velocity, okay. So the opposing torque is proportional to the differential angular velocity. So we can write it Tb is directly proportional to d by dt of theta 1 minus theta 2. Or we can write Tb is equal to capital B into d by dt of theta 1 minus theta 2. So by Newton's second law, we can write applied torque equal to opposing torque, that is T equal to Tb equal to B into d by dt of theta 1 minus theta 2. This is the case of a dashpot when there are angular displacement at both ends. And next element is spring. Okay. So consider an ideal elastic element, that is a torsional spring with a constant spring constant K. And when we are considering that spring, we are assuming that it has a negligible moment of inertia and friction. So the applied torque is T, and due to that torque there is an angular displacement theta. So we can write applied torque is capital T, and there will be an opposing torque due to elasticity of the spring. So the opposing torque due to elasticity of the spring is represented as capital T suffix K, that is Tk. So Tk is the opposing torque due to elasticity. So we can write the equations, torque balance equation, as Tk is directly proportional to theta, or we can write it Tk is equal to K into theta. By Newton's second law, we know that applied torque equal to opposing torque. So we can write capital T equal to Tk equal to K into theta. This is the case of an ideal torsional spring. So in that case, the torque balance equation is T equal to Tk equal to K into theta. This is the case of a mechanical rotational system. If you remember when we discussed that in the case of a translational system, what are the equations? F equal to Fk equal to K into X. That was the equation. Okay. In the case of rotational system, it is T equal to Tk equal to K into theta. So next we are considering that when we are applying a torque capital T, the spring has displacement at both ends. That means it is shown in this last figure, that is the displacement at one end is theta 1 and the displacement at the other end is theta 2. Okay. So we can write the torque balance equation as Tk directly, we can write the opposing torque equation as the Tk is proportional to theta 1 minus theta 2, Tk is equal to K into theta 1 minus theta 2. That is, by Newton's second law, we can say that applied torque is equal to opposing torque. So T is equal to capital Tk is equal to K into theta 1 minus theta 2. These all are the equations corresponding to idealized elements. So the idealized elements are mass, spring and dashpot. In rotational case, we will notate it by torque, moment of inertia, angular displacement theta, etc. And we can write the idealized equations by using torque equations. So in the case of mass, the torque equation is T is equal to Tb equal to B into d square theta by dt square. In the case of mass, it is J into T equal to J into d square theta by dt square. In the case of dashpot, T is equal to Tb is equal to B into d theta by dt, and in the case of spring, it is T is equal to Tk is equal to K into theta. That's all are the equations. Next we can discuss about the guidelines to determine the transfer function of mechanical rotational system. So these guidelines are used to solve the mechanical rotational system. Okay. So the steps are, first step is, in mechanical rotational system, the differential equations governing the system are obtained by writing torque balance equations at nodes in the system. And the nodes are meeting points of the elements. Generally, the nodes are mass elements with the moment of inertia in the system. In some cases, the nodes may be without mass element. Okay. So our aim is to write the differential equation corresponding to a rotational mechanical system. So we will be given by a diagram of mechanical rotational system. So first of all, we have to write the differential equation governing the system. And for getting the differential equations, we are first assuming some nodes in the system. What are the nodes? The mass elements are the nodes of the system. Here, instead of mass, we are using moment of inertia. So, moment of inertia are the nodes of the system. Okay. In some cases, there will not be masses. Okay. So, first of all, we will notate the nodes or moment of inertia of the system, and we will write the differential equation corresponding to each node. Okay. And second rule is that the angular displacement of the moment of inertia of the masses are assumed to be theta 1, theta 2, theta 3, etc. And we will assign a displacement to each mass or node. And this first derivative of the angular displacement is angular velocity. The second derivative of the angular displacement is angular acceleration. So in the second rule, it is stating that first we assume the masses. First we assume the nodes. Nodes are the moment of inertia of the body. Okay, that we will notate it by J1, J2, etc. And next we will assume the displacement, angular displacement corresponding to each of the mass element or moment of inertia, that it is noted by theta 1, theta 2, theta 3, etc. And its first derivative is, what is the first derivative of angular displacement? It is angular velocity. And the second derivative of the angular displacement is angular acceleration. Okay. So in the second step, we are assuming the angular displacement to each of the moment of inertia. Okay. And in this third step, we draw the free body diagram of the system. And the free body diagram is obtained by drawing each moment of inertia of mass separately and then marking all the torques acting on the body. Always the opposing torques act in a direction opposite to the applied torque. So in the third step, it is saying that we will draw the free body diagram of the system. For getting the free body diagram, we are representing each of the moment of inertia separately, and each of the moment of inertia is drawn separately, and we will represent the applied forces or applied torques on that moment of inertia, and also the opposing torques are also marked. Okay, this is it. This is done in third step, that is we will obtain the free body diagram of the system in the third step. And in the fourth case, the mass has to rotate in the direction of the applied torque, hence the angular displacement, velocity and acceleration of the mass will be in the direction of the applied torque. If there is no applied torque, then the angular displacement, the velocity and the acceleration of the mass is in the direction opposite to that of the opposing torque. Okay. In the third step, we will draw the free body diagram of the system. But when we are drawing the free body diagram, and there is some direction patterns, so the rotational displacement is in the direction of the applied torque. So when the displacement is marked in the same direction as that of the applied torque, so the angular displacement and angular velocity and angular acceleration of the mass will be in the same direction as that of the applied force. And if there is no applied torque, then the angular displacement, the velocity and acceleration of the mass is in the direction opposite to that of the opposing torque. Okay. This is a sign convention sign convention when direction convention when we are drawing a free body diagram. So when we are drawing the free body diagram, we have to indicate the applied torque and opposing torques. So the angular displacement will be in the same direction as that of the applied torque. That is the point in the fourth step. And next is the fifth step. In that, for each free body diagram, write one differential equations by equating the sum of applied torques to the sum of opposing torques. So in the fifth step, we will write the differential equations. How we will get the differential equations? We have Newton's second law, and the applied torque will be equal to opposing torque, and based on that we are writing the differential equation. And in the sixth step, once we got the differential equation, we will take the Laplace transform of differential equation to convert them to algebraic equation, and then rearrange the S-domain equations to eliminate the unwanted variables and obtain the relation between output variable and input variable. And this ratio is called a transfer function of the system. So in the last step, we will take the Laplace transform of the differential equation, and we will rearrange that equation in order to get the transfer function of the system. So these all are the guidelines to solve the problem. and will thorough it when you are doing a problem. So these are the guidelines are similar as that we discussed in the case of mechanical translational system. In that case also we have drawn the free body diagram, but in that case we are using the notations as a force F and displacement x. Similarly opposing force as Fm, Fb and Fk, and the free body diagram drawing methods are same as that in the case of rotational system. So but only the notations have some difference. Okay, you got the idea. So here the Laplace transform of, note some of the points, thus Laplace transform of theta is represented by theta of s. Laplace transform of d theta by dt will be equal to s into theta of s with 0 initial conditions. Okay, you know that d theta by dt is a derivative, so its Laplace transform will contain s into theta of s plus some other terms, but